Okay, so this V, right, so there are alternative forms, right, as you have seen already. And so each one, all of them are, equally valid. So you can compute VKL as inner product of U with A star KL, right, so in 2D unitary transforms, right. So we can actually compute this transform matrix, right, VKL for every coefficient as inner product of U with where U is your image, of course, U is your 2D image. This is also the same as V. Okay, this another way to write it is V is equal to A U A transpose, right. That is also equally valid, where you get your all the VKLs through a matrix multiplication. That is also valid. What is also valid is VKL is equal to double sum Mn going from 0 to n minus 1. What was that? A Km Umn ALN. This is also correct, right? They are all equally valid. So some books may use one over the other. But then all of them are equally valid forms. But the one that I like the most is this one where we wrote down V is equal to script A times U, where script A is A Kronecker A. Okay, and this form I feel is sort of the most elegant because it kind of leads the way from 1D to kind of say 2D in a seamless manner, right? This looks like just one walk away. Whereas the others look like they are kind of roundabout. This is like straight. Okay, just as in 1D we had V is equal to AU. Now going to a 2D simply entails us to use a different unitary transform. This is what we call as a 2D unitary transform, and okay, and the script A, right, which is A Kronecker A, and as I said yesterday, right, if you take an image and then you stack it up as this vector V U, suppose you have an image which is of size, let's say n cross n. So you stack it up, so this is your image U, you make it as an n square cross 1 vector, right. You can convert it to an n cross 1 vector. In order to get a 2D unitary transform, you have to look at your A, which is n cross n, which is coming from 1D, take its Kronecker with A n cross n, and this becomes the script A, which is n square by n square, and operate this script A on U. So don't take A n square by n square, because A n square by n square is also there, that is also available. But you can't multiply this with U, which is n square by 1, and claim that I have actually a 2D transform. That will be a 1D transform corresponding to a sequence of length corresponding to this sequence, which is of length n square by 1, right? That would be wrong. Okay, that would be incorrect. So a 2D transform comes as a natural sort of a progression from 1D, simply as a Kronecker of the 1D unitary matrix with itself. And the whole idea is that once you set this all up, then we don't have to spend additional time, okay, after each one of these, right? Because then simply a matter of replacing DC by an appropriate matrix. So we keep replacing A. If it is DFT, then we replace it with phi. If it is DCT, we replace it with something else, right? If it is whatever, right, slant, we replace it with something else, right, and so on. And we also saw that, so just as we had here U is equal to A Hermitian V, right, which made our entire task very simple, right? Because taking the inverse is like just compute the Hermitian of the forward transform. Similarly here yesterday we showed this, right? We showed that U is script A Hermitian V. I hope we showed this right yesterday, where script A Hermitian is simply the inverse of script A, right? So all of this works out fine. And then we also saw that the columns of this guy will contain, columns of A Hermitian contain the basis image, so A star KL in a vector form. Vector form in the sense that, right, because you also ordered your image, right, in that form, therefore these images are also sitting in that order, and therefore, right, it's simply a matter of taking, suppose you had an n square by 1 column, Just no, you can imagine that is an n cross n in image, right? So just take the first n entries, put it as the first row, right? Second n entries, put it as the second row, and so on, and then right, that gives you back your image. So even though this may look like a column, but you know that the basis images are all sitting as columns of A Hermitian. Okay, so so all of this, right, if it has sunk in well, okay, then we can kind of move forward. Yeah. Same thing, same thing. So there also, right, just as you have a basis image, if you look at A, right, you still haven't kind of taken the transform, right? If you look at the DFT matrix, only after you apply it on some signal, you get a kind of a spectrum. Similarly here, so script A contains that is, if you look at A Hermitian, this is containing the basis images, right? So if you think of it as really a DFT, a 2D DFT, then it will have a complex basis, right? I mean, if you go like above 2, then that basis is not going to be real, but even in 1D that's true, right? You have a complex basis, and then again, right, you can kind of think about a magnitude spectrum, you can think about a phase spectrum, just like you have in 1D. All of that is the same, the way you have it in. Oh, for an image, what is the interpretation? Oh, the interpretation is that how does your intensity change with your spatial coordinates? In time, we say how does the signal strength change with time, right? That is what we mean by, that is the interpretation of frequency, right? In 1D, in 2D, there is no time notion, right? There's only x and y. So it's like saying along the spatial coordinates, how does your intensity change? If it doesn't change anywhere, okay, then it means it's like a kind of a DC image, right? If it won't change at all, suppose it's simply a constant all over, okay, then it means that it has only a DC component. If it has some variation, suppose you make it vary as a sinusoid, right? Then it will mean that it'll have a single tone. If it is something that's a combination of sinusoid, then same thing. Whatever you do in 1D, same thing. Just that the interpretation is here it is varying with spatial coordinates. If you had a video, then you would say how does it vary not only with respect to spatial coordinate, but also right, with respect to time. So we'll have omega, nu, and whatever, one more axis, right, psi. What do you do? Where in the okay, well, we haven't even reached the Fourier transform yet. The Fourier transform, so the omega, right, suppose you talk about it as omega comma nu. So omega will tell along x-axis what is the variation, nu will tell along, let's say, y-axis what is the variation of the intensity as a function of y, and omega will mean what is the variation of intensity as a function of x, right? So if you have a signal, for example, maybe I can show you some examples and then that will make it more clear. We haven't even hit actually DFT yet, right? Of course, I can see that you're inquisitive because that is something that you can map onto, right? Okay. Okay, right. I mean, simply as an aside, right? Let me just ask this. Since we are on there is a Kronecker thing. Okay, in general, right? If I yesterday, right, I showed this property. We said A Kronecker B. Right, inverse is A inverse Kronecker B inverse, right? If A and B are not square, let's say, if A is actually a rectangular matrix, and so is B, can A Kronecker B be square? A is rectangular, B is rectangular. Can A Kronecker B be square? It can be, no? What kind of matrix will that be? A will have, let's say, A is not square. So what, M cross N and N cross M, right? So something like that. So M cross N, this will be N cross M. Okay. So now suppose, right, I'm just trying to ask you, right? Can this be independently valid? I mean, because if A is rectangular, then of course you can't take its inverse, right? But A Kronecker B looks like it's a square now. Okay. If I choose like that. Now, will this mean that I can actually invert A Kronecker B? No, right? Why? What will be the rank? Minimum of, right? Exactly. So the rank of this guy is going to be Mn, right? I mean, max of Mn, right? If A Kronecker B is of size Mn cross Mn, so it can only have a maximum rank of M into N. This guy is rank. Suppose we assume something, right? M is let's say larger than N. Then this guy can have a maximum rank N. Okay, this guy can have a max rank N, correct? B. So the rank of A into rank of B is N square. whereas Mn, right, is of course a number which is which is actually wait a minute, right? So what happened? So Mn is a number which is actually larger than n square, no? And rank of A Kronecker B can only be rank of A into rank of B. It can only be n square. It cannot be m into n, right? M into n, because m is greater than n. It's definitely greater than n square, and therefore, right, you cannot invert. So therefore, this condition, right? I mean, I just thought, right? You might just want to kind of. It has various implications, right? I mean, if you just look at it a little more seriously, it's an interesting property. And by the way, right, some people, for those of you, right, who might be interested, there is also something called, what is that called? So they solve it as an optimization problem. It's called, for those of you who are interested, it's called, I think it's called, a Kronecker product, nearest KP problem. Okay, so it's like saying, suppose I give you, anyway, right, I mean, this is not part of this course and all. I'm just saying, suppose I had a matrix A, right, and suppose I wanted to do a decomposition such that, right, norm of A minus, let's say, C Kronecker D, right, I want to find out matrices C and D such that the Frobenius norm of square, right, of this is as small as possible. Okay, these are the kind of problems that these people actually solve. I mean, is there a unique way to do this? In fact, singular value decomposition, all this is actually typically used. In fact, people do a rank 1 approximation. If you instead of a matrix, if you had a vector here, right, then it will be like a rank 1 approximation. Yesterday we said no, that A star KL, right? Somebody said it's rank 1, right? So you can in fact have, instead of a matrix, suppose you had some A Kronecker B, where B that is A. Okay, now suppose you said that so if it was a vector, right, so you had A into B sort of say transpose. Okay, then you can ask, so if you do something like this, then this is a rank 1 approximation, right? So you can use SPD, right? You people know that SPD can be used for a rank 1 approximation, and also so around this, right, there are so many other things, right, for those of you who are interested. Anyway, so we will move on. Okay, we will take up a DFT now.